There is only one problem for the tutorial this week. We have a system with 2 degrees of freedom, a simplified model of a bicycle with its rider is shown in this figure. Find the vertical motion of the rider when the bicycle hits an elevated road, as shown in figure. Here, we have a system of 2 degrees of freedom. The coordinates can be considered x1 and x2, and the system is subjected to, in fact, a step function with amplitude 0.05. So we need to extract the equation of motion for this system. We use the Lagrange equation to extract the governing equation, and then we can solve the free vibration response and obtain the natural frequency and mode shapes. And then by using the modal analysis method, we can obtain the response to this, in fact, external loading or the base excitation, which will appear as a non-homogeneous term in the equation of motion. So first, let's extract the equation of motion. For this purpose, we can write the kinetic energy and potential energy. As you see, we have the kinetic energy, which is equal to, we have two masses, m1 and m2. So we will have two terms in the kinetic energy, half m1 x1 dot squared, because the velocity is x1 dot. And for the m2, the velocity is x2 dot, half m2 x2 dot squared. The potential energy is the potential energy in the spring K1, which is half K1 x1 minus x2 squared, and the potential energy in the spring K2, half times by K2 x2 squared. So we can substitute into the Lagrange equation to extract the equation of motion. And in the matrix form, we will have two equations with order 2, two ordinary differential equations from order 2. The matrix M and K, you can substitute the numerical value for M1, M2, and K1 and K2. And then by calculating the determinant of the matrix of coefficient, this matrix, we can extract the characteristic equation, and the roots of this equation will be the frequency of the system. The first frequency, which is the fundamental natural frequency, and the second frequency of the system. Now we can extract the mode shapes by substituting into the equation. You know, we have the matrix K minus M omega squared. K minus M omega squared will be a matrix like this. The first component of K, which is 100 minus M omega squared, and the M component is 80, so minus 80 times by omega squared. The second component is minus 100. The corresponding component in matrix M is 0. The third one is again minus 100, and again the corresponding component in matrix M is 0, this term. And finally, the last component, which is 150 in matrix K, minus M omega squared, and the corresponding component in matrix M is 40. So it will be 40 times by omega squared. This is the matrix of coefficients, and it must be multiplied by the amplitudes x1 and x2, and the right hand side of the equation, because this is the free vibration equation, is 0. So from these two equations, we can extract a relation between x1 and x2. From the first one or second one, no difference, both of them will give you the same. So from the first one, for example, we will have 100 minus 80 times by omega squared times by x1 minus 100 times by x2 is equal to 0. So from this equation, we can find the relation between x1 and x2. So x1 is equal to 100 divided by 100 minus 80 omega squared times by x2. This is the relation between x1 and x2. And now if you substitute omega is equal to omega 1, you can extract the first mode shape. We obtain that here. You can see that we obtain that x1 is equal to 1.366 x2, and when you substitute omega is equal to omega 2, which is 68.3 here. If you substitute omega is equal to omega 2, you can extract the second relation. Of course, I should mention here we had 100, I think, kilonewton. Yes, this is 100 kilonewton and 50 kilonewton. So in the matrix of, in this matrix K, we have multiplied by 1000, okay, because this is the kilonewton and we need to substitute. And here instead of 100 and 115, instead of these terms, we should substitute 100 multiplied by 1000. Okay, so we can simplify and obtain the relation for x1 and x2, and this is the mode shapes. The next step, we need to normalize the mode shapes by using the matrix M. For this purpose, we calculate the x transpose multiplied by M multiplied by x for x1 and x2 for the first and second mode shape, and we can calculate the value of the amplitude, and by using this we can normalize the mode shapes. The first and second mode shape can be normalized, and then we can form the modal matrix, which is a matrix include the first column of this matrix is the first normalized mode shape, the second column is the second normalized mode shape, and we can form this matrix. The vector ft is 0, but we have some initial condition. I mean, here in the system we considered this change in the displacement, we considered it in the initial condition. So if you consider this in the initial condition, the matrix F, the external force is 0 and 0, but the displacement for initial displacement for both terms is 5 centimeter or 0.05 meter, and the velocity is 0. So we can calculate the initial velocity, the vector qt, which is the non-homogeneous term in the modal analysis method, and it's equal to 0 because ft is 0 here, this term. We can calculate the initial condition x. The initial vector for the displacement is 5 centimeter and 5 centimeter, but the initial velocity is 0. So the initial displacement vector can be calculated by this formula, x transpose multiplied by m times by the vector x naught, and the initial velocity can be calculated from this equation, x transpose multiplied by m multiplied by x dot at t is equal to 0, because this term is 0, so q dot will be 0. And now we have the initial condition, we have the external term, and we can calculate the response by using the STOF system equations. We will have similar two STOF systems. So for each of them, we can obtain the response. For the first one, Q1T is Q10 cosine omega 1T, and Q2T is Q20 cosine omega 2T. And then by using the matrix and vector algebra, you can calculate the xt, and you can extract the response for xt, which is equal to the modal matrix multiplied by qt. We have q1 and q2, so you only need to multiply the modal matrix by q1 and q2 and calculate the response for xt. Okay, this is the tutorial for this week, and by this one we can wrap up the tutorial sessions, and it will be finished. Okay, thank you for your attention.